Hello friends, in this video I am going to explain another deletion in the AVL search tree, and which will require an L rotation to be performed in the deletion process in order to restore the balance of the AVL search tree. So we have just taken an example AVL search tree on the board, and we'll perform a deletion in a way so as to apply the L rotation or the left rotation. What will be the case of the L rotation, I will just tell you in a bit. And this L rotation is to be performed on this AVL search tree after the deletion of some of the nodes. So if we delete, suppose if we delete from this figure this 18, if we assume it to be an AVL search tree, first let us verify the balance factor and confirm whether it is an AVL search tree. So this is the balance factor of this 68 is 0, this is 0, this is 0, because all of them are leaf nodes. So this balance factor is 1, this balance factor is minus 1, this balance factor is 0, this balance factor is 1 minus 0 means 1, this balance factor is 2 minus 3 means minus 1. So this is the AVL search tree because all the balance factors are lying within the permissible range of values. So in this case, if we delete, suppose this 18 from here, if we delete this 18 from here and see what happens, then we will be able to understand what we are going to try to explain in this video. So suppose we will get this 18 deleted from this AVL search tree. So I will write delete 18. So after deletion of 18, the AVL tree will look like somewhat like this: 46 rather, 20, this should be unchanged, this portion will remain unchanged, 54, 50, this is how much, 48, this is 50, this is 60, this is 68. So this is the AVL search tree after the deletion process, and we'll just consider this 18 to be present over here. Not at all present because it has already been deleted, but it will be just, I will just write it in a dotted format so as to make it a bit different from the other nodes which are existent, and this has been deleted. So in order to show that it is deleted, not present, I will just use the dotted representation. So after the dotted representation, I will write this 18 to assume that 18 is now over here. So if we just start our backtracking procedure and see, first we need to find the balance factors after the deletion of 18. So this is 0, this is 0, this is minus 1, this is 1, this is 0, this is, there is no left and right subtree, so this will be how much? This will be 0, and this will be 1 minus 3. So 1 minus 3 is minus 2. So this 46 has a balance factor of minus 2. Now we will start the backtracking procedure starting from this 18 and see whether we encounter any balance factor which is deviating from the permissible range of values of the balance factors for an AVL search tree. So if we just go on backtracking from this 18 towards the root, and in the backtracking journey we see that if we encounter any balance factor value which is violating the balance factor, which is deviating from the permissible range of values of balance factors, then we will determine, then we will just label that node to be the node A, and see, we will just go on backtracking from this 18. We see that the balance factor over here is 0, that is well and good, and after that we go to this 46 and see the balance factor is minus 2, which is deviating. So this deviation makes it to be labeled as A. So this is the node A, and we'll see where the node containing the value 18 has been deleted with respect to the node A. So with respect to node A, we see that the deletion has taken place from the left subtree of node A. So the deletion has taken place from the left subtree of node A means we will have to apply a left rotation, an L rotation, in order to restore balance to the AVL to the AVL search tree. So excuse me. So this 18 is on the left subtree, so it will be a L rotation, and we will, for this L rotation, we have to see the immediate right child of A and label it as B and see what is the balance factor of B. The balance factor of B is 0. The balance factor of B is 0. So this balance factor of B means B is 0 means we have to perform the L0 rotation. So L0 rotation is needs to be performed in the case where we have deleted the 18 in this manner. So L0 rotation can be done in a similar manner as it will be reminiscent of the fact of RR rotation which we performed in the case of insertion in the AVL search tree. It is quite reminiscent of that fact, but it is not at all the same thing. It is not the exact thing, but we can just keep it in mind, bear it in mind, in order to remember this, that it is quite similar to the fact that quite similar to the method which we applied in the case of the RR rotation, that is we will just pull this node, that is we will pull this node B from this right side in an anti-clockwise manner, so that 54 comes to become the root and this 46 will become the left child of 54. So in this way we can perform the L0 rotation. So L0 rotation, after performing the L0 rotation, this 54 will come over here because we will pull this 54 in an anti-clockwise manner and 54 will be the root now, 46 will be the left child of 54, 20 will be linked to 46 as it was linked in this case, so 46 will be linked to 20 in this way, and 54 is linked with 60, so 60 will become this right child of 54 as it was before, and 68 was linked as the right child of 60 as before in this case also. So 68 will be linked to 60 in the same way as it was linked over here. So this is these are the two parts which have been drawn so far, but there is only another part which is remaining to be drawn, that is this one. So this 50 is linked to the left subtree of 54 and this 50 is the left child of 54, but in the course of this L0 rotation, this 46 has become the left child of 54. So 50 cannot remain the left child of 54 because already 46 has become the left child of 54. So in order to accommodate this 50, we have to accommodate this 50 in such a manner, we have to accommodate this left subtree of 54 in such a manner so as to place it in the left subtree of 54 because it was originally a part of the left subtree of 54. So it will remain as a part of the left subtree of 54, but 50 will not be the 50 will not remain the left child because 46 has already become the left child in the course of the rotation. So this 50 will be accommodated in this way. We will just link this 50 as the right child of 46 and this 48 was linked as the left child of 50 and that will remain as it is. So 48 will be linked in the same way as it was linked with the 50 in this figure. So this is the way we can accommodate the entire left subtree on the left subtree portion of 54 after the L0 rotation has been performed. So this has been shown by this representation. So let's calculate the balance factors to see whether we have restored the balance of the AVL search tree. So this is a leaf node, the balance factor is 0. This is a leaf node, the balance factor is 0. This is a leaf node, the balance factor is 0. So in this case the balance factor is 1 minus 0 is 1. This balance factor is 46 as a balance factor of 1 minus 2 means minus 1. And this 60 has a balance factor of 0 minus 1 means minus 1. And 54 is a balance factor of 1, 2, 3 minus 2, that is 3 minus 2 means 1. So the balance factors which we can see from this figure are all lying within the permissible range of values of balance factors for an AVL search tree. So in this case, in this way we can see that we have restored the balance by the process of the L0 rotation after the deletion of 18 has been performed before and then followed by L0 rotation, which has given an AVL search tree, which has given a perfect AVL search tree having all the properties of AVL search trees in it. So that is it. So this is the explanation of how to perform the L0 rotation. So how to perform the L0 rotation in a case of deletion, as we have done in this example. So if you have any doubts and queries relating to this entire example, you can well post your doubts and queries into the comment section below so that I can address them. Thanks for watching this video.